Okay, to start. So today's lecture will be on mostly on a relation between mapping class groups and braid groups. First of all, let us just I would like to start with a more detailed information on braid groups. I have mentioned them in some previous lectures, but we didn't discuss them in details. So how one can look on mapping class on braid groups? So first of all, usual point of view, the most geometric one, is that a braid is a just as a geometric object. We have a plane with I don't want to okay with several marked points, finitely many marked points, and these marked points, and we have a parallel copy of the same plane. So for instance, in usual 3 space, this is a plane z equals 0, and this one is z equals 1. So we have 2 parallel copies with the same marked points. So they are obtained just by shift, vertical shift. And now we have descending strands. Each strand always go down, so it is not allowed to things like that, and each strand starts from one of the points on the upper plane and finishes on one of the points below, and we get such picture. And braids are studied up to an isotopy up to an isotopy in class of braids. So up to an isotopy such that points, endpoints are fixed, and all strands remain descending through the isotopy. Actually, it is possible to show that the last condition is not important if 2 braids are isotopic just inside this slice between 2 parallel planes, and during this isotopy we allow strands to become non-descendant, then this is still the same equivalence relation, but we will never use this usual point of view that we consider braids up to isotopy preserving descendant of strands. Okay, and what is known about yes, and braids form a group with usual operation. Operation is just concatenation that we consider one braid, and here the second braid, and well, my convention will be that if this is first braid and this is the second one, then this concatenation is multiple products in this particular order. Okay, so this is one point of view. Another point of view is that okay, if we look on this picture and take any intermediate plane, any plane parallel to the original and to the second one, then it intersects our braid in n distinct points. And instead of thinking about n strands, we can think about configuration of n points, which changes as we pass from well, in this direction from, and we get a loop in the configuration space. So we can consider a configuration space of n non-ordered points in R2. So configuration space of such points. So a point in this configuration space is a collection of n non-ordered points in R2, and then braid is exactly loop in this configuration space, starting and ending in one particular base point. Or an important thing for constructing braid groups is that we have fixed these initial points. For instance, it is if we have x and y coordinates in plane, it is convenient to take points I1, 0, etc., and 0. For instance, it is not important how to fix them, but we need to fix the initial set of points to be able to multiply braids. And okay, so loops, braids are exactly loops with well, loops at base point, at chosen base point. Okay, and isotopy of braids is exactly isotopy of loops, since and so the braid group is exactly the fundamental group of this configuration space. This is the second point of view. So we can consider just geometric pictures like that, or we can consider this configuration space. And the third point of view is that the braid group is the mapping class group of genus G surface with one boundary component. As usually we consider when we have a boundary component, we assume that all homeomorphism or diffeomorphisms preserve the boundary pointwise. Why this is true? Actually, this is this is not difficult, but this should be proved. So this is theorem, and let us give a proof of it. First of all,
Извините, там что-то не то написано, в смысле, что у нас слева зависит от n, а справа от n не зависит. Да.
Yes. Sorry. For braids, the parameter is usually denoted by n, and for sorry. It is better to write here. I'm sorry. Here we have n, and here we have. I'm sorry. This the correct we have not a surface of genus G with one boundary component. We have a surface with one boundary component and n punctures, and this surface is of genus 0. So this is actually this S10n. Let us denote it just by dn. It's a disk, as genus G surface with one boundary component is a disk, so this is a disk with n boundary components. Actually, before proving, first let us note that in this situation, when we consider such braids in geometry from the geometric point of view, or we consider these loops in configuration space, then it is not important whether we consider R2 or we can consider a disk. We can choose a sufficiently large disk, and it is obvious that any braid can be just pushed here so that it is throughout the whole path from up to below. It is contained in a disk, and throughout any isotope between two braids, we can also assume that we are contained in a disk. And also here it is easy to see that if we choose endpoints in D2, then this is just a homotopy equivalence. There are no problems about it. So it is better to think here about configuration space of endpoints in D2, where the base point corresponds to configuration of endpoints inside D2. No, we do not want to consider points on the boundary. Okay, so let us prove the theorem. First of all, let us construct a homomorphism from the mapping class group of this n-punctured disk to the braid group. Okay. Look, if we have this mapping class group can be represented by a homeomorphism, orientation preserving homeomorphism from disk to itself. Originally, this is a homeomorphism of n-punctured disk to itself, which fixes boundary pointwise, so it is identical on the boundary. But now, okay, any such homeomorphism permutes punctures in some way, and we can extend this homeomorphism to punctures, so that we may think of this phi as homeomorphism of the whole disk to itself, such that phi preserves the boundary pointwise, and let us denote these punctures by P1, Pn, and phi preserves punctures, but setwise. It may permute punctures. Okay, but now when we look on this homeomorphism phi as when we fill the punctures and we think of phi as of homeomorphism of the disk, let us forget about punctures and now just look on phi as the on the homeomorphism of the disk. Then we know that there is Alexander's trick. This is not Alexander's method. This is the same Alexander, but completely different. Completely different situation. When we have any homeomorphism of disk onto itself, and this homeomorphism is here we have some picture, is fixes boundary pointwise, then we can there is a canonical way to produce an isotopy between this homeomorphism and the identity one. Namely, we start to consider homeomorphisms like that, which are identical on such annulus, and here we have the homocity of phi. So, and this annulus becomes wider, this disk becomes smaller, and eventually we have an identical homeomorphism. So we always have it is not only true that any homeomorphism of a disk trivial on the boundary. It is true that any such homeomorphism is isotopic to the identical one, but moreover, it is true that we have a canonical way to produce such an isotopy. What is the difference between just existence of such an isotopy and a canonical isotopy? Actually, the difference is as follows. If we have just any isotopy, then we can only say that the homeomorphism, we may consider the group homeomorphisms of disks preserving the boundary. If we knew only that any homeomorphism is isotopic to the identity, then it is just we know only that this group is connected. Okay, pathwise connected, but we knew more. We know more. We know that there is an for each homeomorphism there is a canonical isotopy between this homeomorphism and the identical homomorphism. And this implies that this group is contractible. Indeed, if in topological space we have a canonical way to come from any point to the base point, okay, obviously this canonical way depends continuously from the original homeomorphism. So this, in fact, this is contractible. I will. Okay, just one note concerning notation. I always keep in mind that today we always consider homeomorphisms of surfaces with boundary, which fix boundary pointwise. So I just don't want to write it down. So I will write homeo of dn oh sorry, I'm the same is true for dn, but today I need only d2. I just write homeomorphism of d2, meaning that they fix boundary pointwise. Okay, and now how to produce a braid? So we have a homeomorphism. Now let us consider, here we have a disk, and let us consider, here we have here we have no, I don't just I would like to map it onto itself by phi. And now let us consider, sorry, I do it like that. We consider a disk, and I can map this disk to the same disk by phi. The chosen collection of points P1, Pn is mapped to the chosen points P1, Pn here. Now I consider an isotopy. So this will be the time parameter. And for each moment of time, I have got a mapping phi t to the same disk. But now it is not true that it makes marked points to marked points. It's just make this point, send these points to some points in the disk. But on the lower base, we have the identity, and which is phi 1, say, okay, and this is phi 0, and on the lower base we again see that base points go to marked points go to marked points, since okay, since this is the identity homeomorphism. Okay, and if we look on look on the trajectory of every point, then we get this braid. We look on the trajectories of of the images of these chosen endpoints. Okay, and so we get a braid. Why this is sorry. Why this mapping? So we get a mapping, but why this mapping is well defined? The matter is that when we have constructed this braid, we made a choice. We have chosen this isotopy Phi. This was a choice. We could choose it differently, but any two such choices are isotopic to each other. The matter is that this group is not only connected, but it is contractible. So any two choices of isotopies, actually we have a canonical isotopy and we could choose it canonically, but this Alexander's isotopy. But any other choice leads to an isotopic picture. So it is well defined. Well, and actually F is bijective. Why? First of all, why F is surjective? Suppose that we have a braid and we would like to sorry between before stating that it is bijective, of course I need to mention that F is, and this is a good exercise, F is a homomorphism. My agreements were such that this is homomorphism homomorphism, not an anti-homomorphism. And so if we apply two homeomorphisms, two mapping classes, then we get two braids in this particular direction. Okay, but and then F is bijective. First of all, why F is a surjection? F is a surjection because of this is just a version of the proposition on extending of isotopies, which we discussed for even in more difficult situation. We have extended isotopies from curves to surface, but it is even easier to extend isotopies from points to a surface. So if we know how these points should behave through the isotopy, if we are given a braid, then we know how to these points should behave during the isotopy. We also know that the isotopy must be identity on the boundary, so we may always extend this to an isotopy of the whole surface. Okay, so we provide eventually for time, when we consider this isotopy, then for time equals 1, we see not 1 for time. I'm sorry. I must here. I choose here the direction of time so that I start from phi and I end with identity. This was to achieve that F is homomorphism, not anti-homomorphism. So we must look in different way. We must start from identity and finish with phi, and we see that we obtain a homeomorphism which produce the prescribed braid. But well, and why it is injective? Actually, to show, since F is a homeomorphism, we just need to show that if F of some homeomorphism phi is a trivial braid, then phi represents 1 in the mapping class group of n-punctured disk. So this is claim which we need to prove to show that F is an injection. Okay, why this is true? The matter is okay. If what does it mean that F of phi equals 1? This this means that if we consider this procedure for this particular homeomorphism phi, then the obtained braid is trivial. So by an isotopy, we may achieve that this braid is just straight. Okay. So if this is so, then on any level, we see not only a homeomorphism of a disk, of the disk which fixes the boundary, but we see the homeomorphism of a disk which fixes the boundary pointwise and every puncture. So this means that for this isotopy, we see that every such homeomorphism belongs to homeomorphisms of disk of the n. Of n-punctured disk. We may and what does it mean? This means that the original homeomorphism is homotopic to the identity inside homeomorphism of Dn. This is exactly that it is trivial in the mapping class of Dn, in the mapping class group. Okay, so this finishes our claim. So we see that our conclusion is that Braid group is the same as is the same as for the fundamental group of the configuration space of R2. And this is the same as the mapping class group of the sphere with one boundary component and n punctures. Well, okay. Now, before, actually, this is a more or less trivial relation between Braid groups and mapping class group. And today we will discuss a deeper relation, another relation between mapping class groups and Braid groups.
But... Извините, чем мы пользуемся, когда мы говорим о том, что если у нас коса выпрямляется, то тогда это отображение тривиально. То есть тут уже зашито какое-то похожее утверждение на то, что вот, значит, группа гомоморфизмов втягиваемая, тут только что-то другое, что у нас есть непрерывное отображение типа из множества этих, ну, в общем, пространства, P1 от которого это группа кос в гомоморфизм или что-то такое. Здесь же зашито что-то нетривиальное. А что зашито?
Yes, thank you for the question. Actually, indeed, when we make this trivial braid, it is trivial, but we make it straight. We start from a trivial braid and we make it straight. And what is hidden here? Actually, is there something hidden here? Yes.
Вот кажется, что мы пользуемся, что если у нас есть там непрерывное, ладно, извините.
Well, one moment. This is a very good question. In some sense, we actually, we look. There is the following reason why we do not need any deep results here. If we just look at any level, yes, then we see for this we have this trivial braid, isotopically trivial braid, which is not straight yet. We have this set of points or intersection of our level with of course, the matter is that we have a canonical way to move these points to the corresponding point to these points P1, Pn. What is this canonical way? This canonical way, actually, it is here. We may go along these lower parts of these strands and project them onto this intermediate plane. And we get canonical ways to go to this P1, Pn, not just any way, but we our braid prescribes how to go from our points to these base points. And now when we extend an isotopy, we can always extend an isotopy if the initial if the isotopy on given set of points changes continuously, then the extension we may extend it so that it again changes continuously.
Правильно ли я понимаю, что на самом деле у нас утверждение такое, что если из пространства n точек в диске в пространство гомеоморфизмов диска есть непрерывное отображение.
No.
Нет, не оно.
This is not only endpoints. This is endpoint with prescribed way.
Да, но мы же продолжаем. То есть у нас, конечно, есть этот prescribed way, но мы же продолжаем гомеоморфизм. То есть нам нужно, в смысле, не только канонический способ двигать точки, нам нужно канонический способ по точкам, по набору точек выдать гомеоморфизм диска.
Нет, не по набору точек, а по набору точек, для которых указано, как их двигать в P1, Pn.
Ну хорошо, но по набору точек, которые двигать. Но это в смысле, если мы по набору точек умеем выдавать гомеоморфизм, то тогда мы, значит, это естественно, тогда по набору точек, которые мы умеем двигать, есть
Но мы по набору точек не умеем выдавать гомеоморфизм, а по набору точек, которые умеем двигать, умеем выдавать изотопию.
Хорошо. То есть вот такое утверждение.
Once more. Let us stop for a moment on this way. This is an important point, and let us discuss it. So suppose that actually we need one thing. I forget about it. We will see now that there is one important thing. So suppose we have a braid which is trivial, but is not trivialized. So it is not straight. Yes. So for each level, we have in this level we have endpoints. Let them be Q1 of t. T is this level, okay, and Qn of t. But we have also these original points P1, Pn, and they are also somewhere here. P1, P2, Pn. Now, these parts of braid, which are below our, provide us canonical paths from Pn to Qn of t, and from each pk to Qn of t. These are canonical paths, and of course these paths from Pn, pk to Qk of t. Now we may vary this level t this red level T where we took our section. Of course, these paths depend continuously on T. So if we take a closed plane, then of course these paths will be closed. Now we may go from for T from 0 to 1, and we start with identity homeomorphism below, and we have this sorry. We have this homeomorphism on, we have these paths are isotopies for on points Pn, P1, Pn. And we may extend these isotopies to homeomorphisms, to the isotopy. We may extend this isotopy to the isotopy of the whole. Oh, so sorry. And this is again surjection. I'm sorry. Well, I'm not right. The matter is that we arrive. If we proceed like that, we may arrive to a different homeomorphism of a punctured disk. Not to the.
Ой, это, кстати, не какая-нибудь теорема клеточной аппроксимации?
Нет, не теорема клеточной аппроксимации. Так, сейчас что-то я запутался, извините. Well. Yes, of course. To obtain that. In fact, we need one deep fact to obtain that this mapping is injective. I'm sorry to forget about it. Yes, this deep fact is the following: that if we take the homeomorphisms of n-punctured disk up to the boundary, and we take the connected component of the identity, then this group is simply connected. First, let us understand why this helps us, and second, I will explain why this is true. So yes, when we proceed like that from for T from 0 to n, they then yes, in fact, what I'm trying to do, I'm trying to make an isotopy of an isotopy. What we see here is already an isotopy of the homeomorphism. Originally, our braid is an isotopy between Yes, first of all, starting from Braid, starting from a Braid, we since the sorry, что-то я совсем запутался. Так. Нет, что-то ерунда какая-то. I'm sorry. Let's postpone this question. It is easy, but according to some strange, I can't solve it now. Let's postpone them for a while. Just some easy point, but I forget about it. I'm sorry. Okay, let's proceed with and maybe we'll return to this later. Okay, but thank you very much for the question. It is actually important. So we will discuss why this is the injectivity. We will discuss it later, but now let us proceed. So actually what I am going to discuss here today is so-called Bierman-Hilden theorem, which is a less trivial relation between mapping class groups and Braid groups. And actually it starts from the following observation. Let's consider a genus G surface with one boundary component as G1, and consider the rotation along this horizontal axis by pi. I will call this I a hyperelliptic involution. Actually, this name comes from algebraic geometry. If we have a hyperelliptic curve, okay, let us use complex notation, W squared Z. Then such particular curve is called hyperelliptic curve, and it has involution which just takes W to minus W, and topologically, of course, this complex curve is not a curve with boundary, but a closed curve. But for a closed, okay, if we imagine here that it is a closed curve, this is also possible. Then topologically, this hyperelliptic involution looks exactly like such rotation. So this algebraic geometry is not important for me at the moment. And for me now, the hyperelliptic involution, this is only where this name comes from. But for me, the hyperelliptic involution is just such naive rotation by angle pi. Look, this hyperelliptic involution has fixed points, which are intersection points of the rotation axis with our surface, and we have 2G plus 1 fixed points. And now let us consider the quotient space of the surface by the hyperelliptic involution. And let us look what is this topologically. So first of all, the boundary component will be again the circle, but this circle will be twice less than initial one. Initial circle will come twice along this circle. And now, okay, how to produce this quotient space. Okay, to produce quotient space, we need to cut along such horizontal plane. Delete the lower part, and on the upper part we just glue we glue two sides of every such curve. We glue this one with that one and so on, since they are taken to each other by hyperelliptic involution. And what we get, it topologically looks like, okay, I will draw less number of, I'm sorry, I don't want to draw as many handles as above. So these are images of that green circles. These are the same red points. But now look, topologically, this is just a disk. This is just the disk with 2G+1 marked points. Okay. So it is not surprising that the homeomorphisms of the original surface are related with braids on 2G+1 strands. More precisely, we need to consider not all homeomorphisms, but only those which commute with the hyperelliptic involution. So let us introduce notation. If we consider, actually, I always consider homeomorphisms trivial on the boundary. Yes. So I do not need to care about orientation. Any homeomorphism which is trivial on the boundary necessarily preserves the orientation. So if we consider homeomorphisms of the surface, I remind that I mean that these are homeomorphisms preserving the boundary. Well, we need to be careful here. Note that the hyperelliptic involution doesn't belong to this group, since the hyperelliptic involution is not trivial on the boundary. It rotates boundary by pi. Nevertheless, we may consider the subgroup here. We may consider the subgroup, which is, they are called symmetric homeomorphisms. And this subgroup consists of all homeomorphisms commuting with the hyperelliptic involution. Okay, this is an interesting. Sorry?
Commuting up to homotopy or just commuting?
No, just commuting. Just at the moment we actually, this is the most non-trivial point to pass here from homeomorphism to mapping classes. This is what I want, but at the moment I just consider homeomorphisms, and they are just strictly commuting with the hyperelliptic involution. Look, the most non-trivial part here is that we can consider symmetric homeomorphisms up to isotopy, or we may consider symmetric homeomorphisms up to symmetric isotopy. And a priori, it is completely unclear, is this the same or not? Symmetric isotopy means isotopy in the inside symmetric homeomorphism, so that we may consider two symmetric homeomorphisms, and we may wonder whether they are isotopic, not requiring that the homeomorphism remains symmetric through the isotopy, or we may require that the homeomorphism remains symmetric through the isotopy. And a priori, these are different equivalence relation. What is a simple thing is that when we consider symmetric homeomorphisms up to symmetric isotopy, then this is the same as the mapping class group of the surface below, and hence this is the Braid group. Why? So let us start with this claim, but the most non-trivial claim, this is our goal, is that in fact these two things are the same. So, and all these together, this group is called symmetric mapping class group of the surface. And it is important to have here usual isotopy, so that this is a subgroup of usual mapping class group. And so this is Bierman-Hilden theorem, Bierman-Hilden theorem, that finally we will have that the symmetric mapping class group of the surface is isomorphic to the Braid group. Yes, and moreover, it is also true that this symmetric mapping class group is exactly those mapping classes which commute with the hyperelliptic involution up to homotopy, but we will discuss this later. Let us now start from this. But okay, let us start with an easy part. Easy part is this one, that if we consider symmetric homeomorphism up to symmetric isotopy, this is the same as homeomorphisms of the surface below, preserving punctures, setwise up to usual isotopy. Okay, actually, this is more or less obvious. The matter is of course, suppose that we have a symmetric homeomorphism upstairs, then downstairs on this it induces a homeomorphism, of course. Vice versa, suppose that we have yes, and the symmetric homeomorphism always preserves these fixed points setwise. Okay, if we have a symmetric homeomorphism here, then we immediately produce a homeomorphism below, which preserves these points setwise. So let us fix this, that we have this mapping even not on the level of mapping classes, but on the level of homeomorphisms, that symmetric homeomorphisms of genus G surface are in one-to-one correspondence. There is bijection, canonical bijection. With homeomorphisms of disk with 2G+1 punctures. Actually, I didn't explain yet. I haven't explained yet that it is bijection. What I have explained is that we have a mapping here. But now look, suppose that we have a homeomorphism downstairs. Then so we have I just would like to turn down. Okay, we have a homeomorphism of this disk onto itself, which preserve the puncture setwise. Let us try to lift this homeomorphism upstairs. Well, upstairs for each point, we have its image here. For each point x here, we have its image, let it be projection pi. We have pi of x, and we may apply this homeomorphism downstairs, phi of x, and we have 2 points, 2 pre-images of phi of x. So the only thing to construct the homeomorphism upstairs, we need to choose to pick one of these 2 points. But look, on the boundary, we have already a canonical way to pick one of the 2 points. The matter is that we consider only homeomorphisms that are identity on the boundary. So on the boundary, we have no freedom. We just need to make our homeomorphism the identity. But now, so on the boundary, we have already picked one of the 2 points. Now we may travel along this surface, and well, okay, this is usual lifting property for the covering. Out of these 2G+1 points, this is just usual covering, and starting from this, we may choose one of the 2 images, and the only thing which we need to understand is that this is well defined, that Okay. Suppose that suppose that the well, the precise picture as follows. If we would like to understand, so we have homeomorphism phi downstairs, and I would like to construct phi tilde upstairs. I know that phi tilde is trivial on the boundary, and now I would like to consider to construct phi tilde of x. So I proceed like in the following way. I choose any curve, any arc from the boundary to the point x. Below, I see the curve, the curve from the boundary to pi of x. Now I apply here is this curve is this arc is alpha, this arc is pi of alpha. Now I apply the now I apply the homeomorphism phi, and I get some arc phi of pi of alpha, which leads to this point phi of x. But now I have the only possibility of lifting this arc upstairs. So this is the lift of phi of pi of alpha, and when I lift it, I see that I come to one of the pre-images of phi of pi of x, and this one must be chosen for phi tilde of x. Why this is well defined? What do I need to check? I need to check that suppose I could choose another curve alpha, for instance, this one, and I get another, this alpha prime, and I get another curve downstairs, and what I need to understand that I still come to the same 5 tilde of x. And the reason is the following, that since alpha and alpha prime, look on this picture here. I have this pi of alpha, and I have this pi of alpha prime. Since the both of these curves lead to x, to the same x. Look, our covering is has twofold branching at every of these marked points. So passing around any of these branch points changes our leaves, our two leaves. This means that we have even number of marked points in between. This is not very good claim. The matter is that these two arcs can be intersecting, but we have algebraically even number of marked points. We may just count how many times we could pass to one-dimensional homology, and look how many times this loop consisting of two arcs goes around any point. And algebraically, we have even numbers of marked points in between. So we, because the lift of this loop is connected, is closed. And this property remains true after the homeomorphism phi. So similarly, here we have this we have here sorry. So here we had this pi of a alpha prime, and then we apply the homeomorphism phi to both these arcs, and we get another this phi of pi of alpha prime. And again, after the homeomorphism phi, between so we have even numbers of points in between pi of alpha and pi of alpha prime, and hence we have even number of points between phi of pi of alpha and phi of pi of alpha prime, and hence they again this the corresponding curve again remains closed upstairs. So they lead to the same phi tilde of x. So we actually have this bijection on the level of homeomorphism. So it is not on the level of mapping classes, but it is just on the level of homeomorphism. And yes, and of course, symmetric isotopy here is just the same as isotopy here. This is completely trivial. Okay, isotopy is given at any point, at any moment. Isotopy is just a vector field which shows how points move. And if we have such isotopy, symmetric isotopy upstairs, then this is again such vector field downstairs. So we indeed have the same for quotients. So I have explained this easy part. Now let us make a 10-minute break, and after that we will discuss this much more interesting part. Okay, so 10 minutes break. Well, меня слышно?
Да, слышно.
Well, let's proceed. First of all, let us return to this question on trivial braids. I'm sorry, actually there is nothing difficult here at all. Once more, we have constructed a homomorphism, and we have understand that it is surjective homomorphism. Actually, why it is injective? It is very easy. In fact, we do not need anything here, anything deep here. Look, take any phi in the kernel. And what we see here is that this phi we have isotopy between this phi and identity. Yes, and this isotopy yields a trivial braid, but maybe not straight. Our only difficulty was that we would like to have that this braid is straight. If this braid was straight, then phi is isotopic to the identity. In the group of homeomorphisms of this punctured surface, and then phi is trivial in mapping class group. Yes, of course, I mean that phi is a homeomorphism that represents a class in a mapping class group. But if this braid was just straight, then this phi would be trivial in mapping class group. But okay, what does it mean that the braid is trivial? The braid is trivial means that it is a trivial loop in configuration space. Equivalently, it means that this braid is isotopic to straight braid, but it is, I would say, level-wise isotopic. It is isotopic so that every level remains here. Every level, points on every level remain on the same level through the isotopy. And now what we need, we just need extension of isotopy, but extension of such level-wise isotopy. I would like to apply this extension. Just we need to apply it not in any level, but we need to apply it to the whole isotopy. We have isotopy on this number of strands, and we would like to extend it to the whole cylinder, to three-dimensional situation. So the only difficulty here is that we before we always use extension of isotopies only from dimension 1 to dimension 2, from dimension 0 to dimension 2. Here we need to pass from dimension 1 to dimension 3, and of course we may make this extension. And if we look through the proof of the extension of isotopy, we see that if the isotopy is level-wise, then extension can be chosen level-wise as well. Just all vector fields can be chosen horizontal. and that's also, in fact, we at this point we do not need anything else. And after the braid is straight, we see that this phi is trivial in the mapping class group. Okay, let us return to our Bierman-Hilton theory. We have proven this easy part. Before coming to difficult part, let us discuss two more situations. There are two other versions of this situation. Here we have a surface with one boundary component and this hyperelliptic involution. There are two other important situations. First of all, we may consider a surface with two boundary components which are symmetric with respect to the hyperelliptic involution. So we see again iota is rotation by angle pi, but now we have two components which are swapped by the involution. Now we have not 2g plus 1 but 2g plus 2 fixed points, and again below we have disk with 2g plus 2 points, punctures. Yes, these two components are taken to each other in by the involution. So downstairs we have only one boundary component. So this is surface with one boundary component, genus 2 and 2g plus 2 punctures. And again, all the same can be all the same the same argument works. And first of all, again, Bierman-Hilton theorem says that in this situation we again have symmetric mapping class group. Now this is S2G of genus G surface with two boundary components. Again, it is isomorphic to the braid group, but now the braid group of 2G plus 2 strands. But okay. Now the situation, yes, again, we have not proved this yet, but our proof of this part extends to that case immediately. So again, we already know that symmetric homeomorphisms up to symmetric isotopy are in one-to-one with mapping class group of surface of genus G with 2G plus 2 punctures of the surface downstairs, which is the braid group. So we already know this, and this we need to prove that symmetric homeomorphisms are symmetrically isotopic whenever they are isotopic. And one more situation, maybe it may seem that we should start from it, but it is somewhat more difficult. This is a situation of a closed surface. Again, we have hyperelliptic involution, but no connected components at all. First of all, we see here we again have 2G plus 2 fixed points. Well, and what is below? Now this is not a disk. Now we have no boundary component at all, but again we have a surface of genus 0. So downstairs we get a sphere with 2g plus 2 punctures. Not punctures, marked points actually, but we are free to choose from them. It is better to say marked points since, okay, if we have punctures, then these fixed points upstairs, they are mapped to marked points. So it is better to think of them as of marked points. Okay. So downstairs we have surface of genus 0 with 2g plus 2 punctures. Well, there are two things which are different in this situation. First of all, okay, here we have the mapping class group of the sphere with 2g plus 2 marked points or 2g plus 2 punctures, but this is not a disk with punctures. This is a sphere with punctures. Hence, this is not a braid group. Okay, but still, it is some group which is rather close to braid groups. Second, we do not have such isomorphism. The matter is that, look, what is different here? The difference is that we have no, this argument with lifting of paths doesn't work properly. The matter is that we do not have a boundary. Hence, we do not know how to start our, when we try to lift a homeomorphism downstairs to a symmetric homeomorphism upstairs, then we have two possibilities now to do this. And indeed, in this situation, the hyperelliptic involution iota itself belongs to symmetric homeomorphisms of our, first of all, in this situation, it is we need to care of orientation, since in the previous situation we had boundary components, and hence every homeomorphism fixing boundary pointwise is orientation preserving. Now this doesn't work, so we need to consider only orientation preserving homeomorphisms, and now the hyperelliptic involution itself belongs to these homeomorphisms. Hence, and look, this hyperelliptic involution, of course, it induces trivial homeomorphism downstairs. So iota here goes to trivial homeomorphism downstairs. And when we have a homeomorphism downstairs and try to lift it upstairs, then to a symmetric homeomorphism, we have two possibilities, since we have two possibilities for some point, and after we have chosen between them, everything works in the previous situation. So the correct formulation here is that we have symmetric mapping class group of a closed surface, and we must take the quotient by the class, or the mapping class of this hyperelliptic involution, and only after that it is isomorphic to the mapping class group of sphere with 2G+2 punctures. Okay. And again, we again see that in this situation, we also know that symmetric homeomorphism up to of SG up to symmetric isotopy. These are isomorphic to the mapping class group of 2G+2 punctured sphere. So we only need to understand that in all three cases, in all the three cases, we have proposition that two symmetric homeomorphisms phi and psi are symmetrically isotopic whenever they're isotopic. So if we prove this proposition, this will finish the proof of the Biermann-Hilden theorem. Okay, we will prove this theorem, this proposition in the case of surface with one boundary component. The proofs in two other cases are completely similar. Well, so first of all, let us note that we may assume that psi is just the identity homeomorphism. Indeed, if we have, if we have two homeomorphisms which are symmetric, two symmetric homeomorphisms that are symmetrically isotopic, then we may apply psi inverse to this. So we may consider psi inverse composition with phi and identity psi inverse composition, which is psi inverse composition with psi. And of course, the homomorphism psi inverse takes the isotopy between phi and psi to the isotopy between psi inverse phi and identity. So we know that these two homeomorphisms are also isotopic. But so if the proposition is true in this situation, then we can deduce that these two, that there is symmetric isotopy here, that these two homeomorphisms are symmetrically isotopic. But then again, applying psi, we get a symmetric isotopy between phi and psi. So if we prove this proposition for in case where psi is the identity, then the proposition will follow in full generality. So further, we will prove this for the identity. Well, actually, there are several proofs of this proposition. I will describe a proof from the book. Actually, there is a very good book, Farb and Margalit, a primer on mapping class groups. I have already said about this book as far as I remember, but in this so not many proofs that I have told are from this book, but as far as I understand, the proof which I'm going to talk now is not only from this book, but it was at the moment they included this in this book, it was new. So this is a new proof, which seems to be simpler than previous ones. Okay, so let us start with a preliminary lemma. So we have already understand that we already used Alexander's method, and we understand that to prove something about a homeomorphism, it is or about a mapping class, it is very useful to study its action on simple closed curves. And of course, this should work for symmetric homeomorphisms as well. But for symmetric homeomorphisms, it is natural to look on symmetric simple closed curves. What does it mean? Okay, we would like to consider simple closed curves such that it is taken to itself by an involution. Of course, I mean that alpha is taken to itself by an involution set-wise, since okay, we have only finitely many fixed points, so no simple closed curve can be fixed point-wise. So I always mean that it is fixed set-wise. Actually, there are two types of such simple closed curves. Look, there are curves like that. So for instance, this separating simple closed curve is taken to itself by an involution. And also there are curves like this. Okay, sorry. Well, for instance, this one. Curve in horizontal plane, which passes through two. Yes, again, at the moment, I mean that a curve is, I mean a curve, not an isotopic class of a curve. So a curve is just a subset of a surface, and it is, we consider a curve which is taken to itself by the hyperelliptic involution. So this green curve is taken to itself by the hyperelliptic involution. And look, there is these are two principally different situations. For a blue curve, it does not pass through the first curve doesn't pass through fixed points, and the second curve passes through two fixed points. And actually, an easy lemma is that any non-separating simple closed curve passes through exactly two fixed points. So this blue one is separated, so it is it is allowed for a separated curve not to pass through a fixed point, but any non-separating must pass through exactly two fixed points. Let us prove this. first of all, well,
Any non-separating symmetric closed curves passes through to fixed point.
any non-separate. Sorry, what was word?
In the lemma, do we need that the curve is symmetric?
Oh yes, of course. Yes, this is the most important. Of course, and any non-separated symmetric. Yeah, yes, thank you very much. Of course, this is lemma about symmetric simple closed curves. So we study only symmetric simple closed curves, and the claim is that any non-separated symmetric simple closed curve passes through exactly two fixed points. Well, first, let us understand that why it must pass through at least one fixed point, and then why exactly two. Look, I will consider the following chain of symmetric simple closed curves. Look, okay, well, I have here, I have this is one particular chain of symmetric simple closed curves: C1, C2, C3, C4, and so on, C2G. I would like to consider their homology classes, so I would like to orient them. It is not very important how to orient them. Okay, I orient these curves counterclockwise and let their homology classes. Well, in fact, I just like to say I don't want to think about orientations. I just would like to say very easy claim that the homology classes of these 2G simple closed curves generate the first homology group of our surface with one boundary component with the integral coefficients. Okay, this is more or less obvious. We just if we consider this is a good exercise, just to consider cellular decomposition and understand that this is indeed a base. Actually, they form the basis of this group is, of course, isomorphic to z to the power 2g, and this is the basis. Look, hence, let us recall that if gamma is non-separated simple closed curves, as a non-separated simple closed curve, then its homology class is primitive. We have discussed this. Hence, there is I such that the intersection index, algebraic intersection index, is odd. So it is completely impossible for a primitive homology class to have even intersection indices with all elements of the basis, since the intersection form is unimodular. Okay, and now look, suppose that we have I would like to draw it in more details. Suppose that we have we may make all our curves smooth and intersecting transversally. This is not a restriction. Suppose that we have a fixed point. Then if we have transversal intersection of 2 points, say of some gamma and of one of CIs, then in this intersection point we will have it will count with coefficient plus or minus 1 in this intersection. But all other intersection points, all intersections that are not fixed points they are divided into pairs. If since both gamma is a symmetric simple closed curve, any its intersection with CI has well, it has a symmetric intersection. So this is a general observation that if we have two symmetric simple closed curves, then their intersections which are not fixed points can be paired off. The set of intersections is taken to itself by the involution iota. Hence, except for fixed points, we have even number of intersection points. So if gamma did not pass if gamma did not pass through fixed points, it would follow that all intersection indices are even. I do not want to care of signs of intersections. It doesn't matter here at all. Just I would like to say that modulo 2 we get 0. So which is impossible since our homotopy class must be primitive, or homology class must be primitive. Hence, gamma passes through at least one fixed point. Okay, is it possible that gamma passes through exactly one fixed point? Of course not. If we now next we suppose that I just want to draw a neighborhood of a fixed point. If gamma passes through a fixed point, what we see downstairs. Downstairs, we have twofold branching at this fixed point. Hence, downstairs, these two parts of gamma are identified with each other. And what we see that gamma downstairs looks like an arc, gamma bar, which passes through, which comes from this marked point with endpoint in mark point. Okay, but an arc cannot have a single endpoint. It must have another endpoint. So once we have understood that this arc, that gamma passes through at least one point, we see that it must pass through another endpoint. And now the numbers of these two, and now there should be exactly exactly two such endpoints. Why? Okay, so we know that at the moment we know that there are at least two fixed points on gamma, but now, okay, gamma starts from a fixed point, and in some time it comes to another fixed point. So, but let us look on another let us go in different direction on this. We go along gamma in one direction, and now I suggest to go in the other direction from these first fixed points. But this arc and that arc are taken to each other by hyperelliptic involution iota. Hence, the endpoint must be the same. So we see that there are exactly two fixed points. So when we start from the first fixed points and go in one direction, we arrive to the second endpoint, and go in the opposite direction, we arrive again to the second fixed point. So for each non-separating symmetric simple closed curve, the picture is like that. Upstairs, we see a curve which passes through exactly two fixed points. Oh, sorry, it's better to draw it. Downstairs, we see an arc which connects two fixed points. So the image downstairs is an arc connecting two fixed points. So this is how non-separating symmetric simple closed curves do look like. But now the main lemma is as follows. So our main goal is to prove that symmetric homeomorphisms are isotopic whenever they are symmetric, asymmetrically isotopic whenever they are isotopic. First, let us prove this for simple closed curves. So lemma is, suppose that genus is at least 2. Then two non-separating symmetric. Okay, let us formulate it as if two non-separating symmetric simple closed curves are isotopic, just without any requirement to isotopy. So isotopy knows anything about the hyperelliptic involution. Then these two curves are, then they are symmetrically isotopic. Okay, why? Yes, first of all, why G must be at least 2? Look, for G equals 1, this is just not true. Let us consider a torus with 1 boundary component, and I would like to consider 2 simple closed curves like that. This one is the first simple closed curve. Sorry. It seems that I'm not true. For well, for this restriction is not important when we consider surface with boundary, but if we would like to prove that the same is true for closed surfaces, but only if G greater than or equal to 2. If we have a closed torus genus 1 surface with then we have 4 fixed points, and now we have 2 simple closed curves, this one and that one. Of course, these 2 simple closed curves are isotopic. These are just 2 parallels of the same torus. Of course, they are not symmetrically isotopic. Why? Since they pass through different fixed points. The property of a simple closed curve to pass through any prescribed fixed point cannot change during symmetric isotopy. So these 2 curves do not pass, are counterexamples for this lemma in case G equals to 1. So the situation is as follows. The lemma is not true if G equals 1, provided that the surface is closed. It actually is true if the surface has a boundary component, but I will prove it only for G greater than or equal to 2. You may consider it as an exercise for G equals to 1. For G equals to 1, the lemma is not true, and so the proof of Bierman-Hilden theorem, which I'm going to say to you, to tell to you, will not be true. So it is a good exercise proof. However, the theorem itself is correct. So exercise proof that this proposition that symmetric isotopy is equivalent to isotropy for symmetric homeomorphisms in case G equals to 1. For G equals 1, okay, now I'm going to give a proof for G greater than or equal to 2. I think you can understand yourself what should be changed in case G equals 1. Literally, it will not work. Okay, let us start with the proof of this lemma. So, proof of lemma. So look, you see, we have the following situation. We have two simple closed curves, two symmetric non-separated simple closed curves alpha and beta here, and downstairs either of these two curves becomes an arc connecting two marked points. And first, let us understand that alpha bar and beta bar have the same pair of endpoints. And it is interesting that this is exactly the point where we need that genus is at least 2. Indeed, in this particular example, this is not true. If these two curves alpha and beta have the corresponding arcs have different endpoints. Why this is true for when G equals greater than or equal to 2? Okay, if G is greater than or equal to 2, then we have at least 5 marked points below. We have 2G plus 1 marked points, so we have at least 5 marked points. This means that we have a marked point which is neither, which is not an endpoint, not an endpoint of either alpha bar or beta bar. So the existence of such marked point is a crucial point here. Suppose that we have a point which is an endpoint of alpha bar, but not an endpoint of beta bar. And now let us consider the following auxiliary arc. Let us connect. I would like to denote it by gamma bar. Let us connect the endpoint of alpha bar, which is not the endpoint of beta bar, with those point which is not an endpoint of either alpha bar or beta bar. And let us consider the preimage of gamma bar. And it is a simple closed curve upstairs. So upstairs we have 3 simple closed curves, 3 symmetric simple closed curves, alpha, beta, and gamma. And what can we see? We see that now I would like to count the intersection points of beta and gamma, and I would like to count the intersection points of alpha and gamma. I claim that there are even number of intersection points of beta and gamma and odd number of intersection points of alpha and gamma. The matter is that alpha and gamma have one intersection in a fixed point. and beta and gamma have no intersection in fixed point. All other intersections are can be paired off, so we have even number here and odd number here. Okay, but the number of intersection points modulo 2 is homology invariant. It is just algebraic. So we have even algebraic intersection number and odd intersection algebraic number here. So this is a contradiction, because our assumption is that alpha and beta, well, alpha and beta are those two symmetric simple closed curve. Our assumption was that they are isotopic, and at least they represent the same homology class. So we get a contradiction, and this is why the situation is as follows. The situation is that, okay, we have marked points, and alpha bar and beta bar are arcs with endpoints in these two marked points. So now let us proceed as follows. First, second, we may put alpha bar and beta bar in minimal position. What does it mean? It means that there are no bygons. It almost means that there are no bygons. Actually, look, if there is a bygon like that, or like that, a bygon between alpha bar and beta bar, maybe if there is a bygon, then there is an innermost bygon, but innermost bygon, there are three possibilities. It may contain no marked points. It may contain one marked point here, or actually there is third possibility, which is the easiest one, that this bygon contains the whole. Okay, we may have a possibility like that. This bygon contains two marked points. Okay, but in this last situation, there is nothing to prove. Note that any isotopy between alpha bar, if we make an isotopy with alpha bar, then we immediately obtain a symmetric isotopy of alpha. If we perform isotopy downstairs, then we get a symmetric isotopy upstairs. So here the number, if we have bygons of these two types, then actually alpha bar and beta bar are not in minimal position. But if we have this bygon, then alpha bar and beta bar are in minimal position. Well, see, so such bygons do not count for arcs. But in the latter case, we see that this is exactly what we want. If we are in this situation, then alpha bar is isotopic to beta bar, and hence alpha is symmetrically isotopic to beta. So this is exactly what we want. So so we may assume that there are no bigons. If there are bigons like that, then we are not in minimal position. If there is a bigon like that, then we are done. So we may assume that there are no bigons. Assume that there are no bigons for alpha bar and beta bar. However, look, upstairs we must have a bigon. Upstairs, downstairs we so here I mean that we perform an isotopy downstairs, which takes alpha bar and beta bar in minimal position. So we changed alpha and beta, but we changed them by symmetric isotopy. So we may consider this case only. Now, upstairs, we know that alpha and beta are isotopic. Hence, their geometric intersection index is 0. However, their number of intersections is non-zero, is at least 2. Well, at least they intersect in 2 fixed points. They pass through the same pair of fixed points. So our 2 curves at least intersect in these 2 fixed points. So they are definitely not in minimal position. So we have a bigon upstairs, and hence an innermost bigon between alpha and beta. Well, look how this bigon can look like. Actually, there are 3 possibilities. Well, all bigons look look like a disk, okay? But here we have 3 possibilities depending on this bigon can have no fixed points. It may contain 2 fixed points or 1 fixed point. But in any of these possibilities, okay, if we go downstairs, then my claim is that downstairs we get a bigon as well. The crucial point is that the restriction of this projection to this disk so claim is that the restriction of projection to this disk is injective. If it is true, then we get a bigon downstairs. Then this bigon upstairs just embeds downstairs, which is a contradiction. So we need only to understand that it is injective. Okay. The matter is that if it is not injective, yes, then when is it possible that it is not injective? It is possible only if some point in delta, is mapped by iota to another point of delta. This point can be either on the boundary or inside. Well, but look, is it possible that and now we should consider several cases. Okay, so suppose that a point x here goes to another point y here, and iota of x equals y. Okay, look, these points x and y. First of all, they are not fixed points. If it is a fixed, if x is a fixed point, then y is equal to x, and this doesn't contradict injectivity. In the first case, it could be the situation that x and y are intersection points. Yes, so we know that both our curves are symmetric. Both our curves are taken to each of them is taken to itself by the hyperelliptic involution. Hence, if x belongs to beta, if and only if y belongs to beta, and the same for alpha. So we have either both of these curves of these points are inside delta, or they are both on alpha, or they are both on beta, or they are both intersection points. If they are both intersection points, let us consider these 4 cases separately. If they are both intersection points, so this one is x and this one is y. Okay. Okay. Look, one more important observation, that for any simple closed curve like that, for any non-separating symmetric simple closed curve, the hyperelliptic involution changes the orientation of this curve. The matter is hyperelliptic involution changes all homology classes. So if x and y are interchanged by hyperelliptic involution, then these then this arc must go to itself. Okay, we have 2 arcs of beta, of alpha, this one is alpha, which connect x and y, but x and y are swapped by hyperelliptic involution. Hence, this arc must go to itself. Under the hyperelliptic involution, but its orientation is reversed. Hence, there must be a fixed point in between. But we know, we know that it is not possible, since through a fixed point, the curve beta also should contain this fixed point. the curve beta contains both fixed points which are on alpha, so there cannot be a fixed point on this arc. So this situation is impossible. Next situation is that x and y are both on alpha. X is here and y is here. The same, x and y are swapped by the involution, hence they are interchanged. Hence this arc between them is taken to itself, reversing the orientation. Hence there is a fixed point on it, which is impossible. And the same for if x and y are both on beta, and the only the last case is that x and y are in the interior of delta. Okay. But then iota of delta must be equal to delta. Okay, the hyperelliptic involution takes alpha to itself, takes beta to itself, hence it permutes connected components of the surface with alpha and beta deleted. But okay, if it takes at least one interior point to interior point of the same component, then it takes the whole disk to itself. Okay, and there is an easy observation. Which is a slight extension, slight improvement of Brouwer theorem on fixed point. Okay, any involution, any continuous one more, any orientation preserving continuous involution of the two-dimensional disk to itself has a fixed point in the interior of disk. It is possible that if we just have a continuous map from a disk to itself, then it may have a fixed point either in the interior or on the boundary. Okay, it is possible that, but even if a map is an involution, then if a map is an orientation preserving continuous involution, then it must have a fixed point inside, which is not impossible since okay, there are no fixed points inside. So okay, this is an exercise. I'm sorry, that my time is finished. So and this exercise completes the proof of the lemma. So okay, why it completes the proof of the lemma? Since we see that the projection is injective, and the beigen upstairs goes to a beigen downstairs.
In the case when these 2 points are in alpha intersected with beta.
Yes.
And the other 2 cases
No.
exercise. Oh, no.
No. I have considered all 4 cases. If they're in alpha cap beta, yes, then we are done. Since this arc is taken to itself with opposite orientation. The same if they are both on alpha. This arc is taken.
And if they are not on alpha and not on beta?
Yes, and this is the last case. If they are inside, then delta must be taken to itself.
Мгм.
As
okay,
connected
okay,
component.
okay.
And this is exactly what I finished. It
Mhm.
is taken to itself, but now it is a continuous involution of disk to itself. This disk is delta. Sorry. And there must be a fixed point inside in this situation. Okay, so I have proved the lemma. Next time I will finish the proof of Bierman-Hilden theorem. And now let us finish for today.
Sorry, why can't there be a fixed point inside the disk?
Well, why there should be a fixed? Why it is impossible to have a fixed point inside of a disk?
Yes.
Well. Well. Indeed, why is it impossible? It's a good question. Actually, it is better to finish the proof here in another way. Suppose if we know that this disk goes to itself, yes, but at the same time we know that hence this arc also goes to itself, since it's the boundary. We know that E of iota of delta equals delta, iota of alpha equals alpha, and iota of beta equals beta. Hence, we see that this arc and this arc are also taken to itself either of these arcs is taken to itself by iota, but now again we know that the orientation must be reversed. If an arc is taken to itself reversing the orientation, then there is a fixed point in the interior of this arc. It is better to finish the proof like that. So we again have a fixed point here, but we have already understood that it is not possible. Yes, any other questions? Well, thank you very much for attention, and sorry, this is.
Will we have a class next week?
No, next, yes. Thank you for this. No, I think that next week we will not have a class.
Okay.
So see you in 2 weeks. Well, goodbye.
Спасибо, до свидания.
До свидания.
До свидания.
До свидания.